Ever wonder what makes up 95% of the universe? Join us on a cosmic voyage to unravel the secrets of dark matter and dark energy, and drift off to sleep, pondering the mysteries of the cosmos. Ready to fall asleep with a touch of cosmic wonder? This video delves into the hidden world of dark matter and dark energy, offering a soothing and thought-provoking journey through the universe. Close your eyes and let your mind drift upward, beyond the ceiling above you, beyond the atmosphere that cradles our Earth, beyond the familiar glow of our sun. Journey with me into the infinite expanse of space, where countless stars twinkle like diamonds, scattered across black velvet, and galaxies spiral in majestic dance through the cosmic dark. As you settle into comfort, breathing slowly and deeply, imagine yourself floating weightlessly among the stars. Here, in this vast cathedral of space, we encounter one of the universe's most profound mysteries, a secret so extraordinary that it challenges everything we thought we knew about reality itself. You see, when astronomers gaze through their telescopes at the cosmos, they discover something remarkable and unsettling. All the stars we can see, all the planets orbiting distant suns, all the glowing gas clouds and shimmering galaxies, all of this beautiful, luminous matter that fills our imagination, represents only a tiny fraction of what actually exists in the universe. The rest, the overwhelming majority of everything that is, remains invisible to us, hidden, silent, unknown. This invisible realm has been given names that sound like poetry, written by the cosmos itself: dark matter and dark energy. Together, these mysterious components make up about 95% of our universe, leaving the familiar world of stars and planets as mere islands of light in an ocean of cosmic darkness. Tonight, as you prepare to surrender to sleep, let us explore these gentle mysteries together. There's something profoundly calming about contemplating the unknown. It reminds us that we are part of something infinitely larger than ourselves, something magnificent and mysterious that extends far beyond the boundaries of our everyday concern. Allow your breathing to slow and deepen as we embark on this peaceful journey through the cosmic dark, where the greatest mysteries of existence wait to be discovered, and where the very fabric of reality holds secrets that scientists are only beginning to glimpse. In the early decades of the 20th century, astronomers began to notice something peculiar. When they observed galaxies spinning through space, the mathematics didn't quite add up. According to the laws of physics as they understood them, these massive collections of billions of stars should be flying apart, scattered by the centrifugal force of their rotation. But they weren't. The galaxies held together, spinning serenely through the void, as if some invisible hand were gently keeping their stars in place. It was as if each galaxy were wrapped in an unseen embrace, held together by something that couldn't be detected by any telescope or instrument. Imagine, if you will, watching a carousel at night. You can see the painted horses and bright lights spinning around, but you cannot see the central mechanism that holds everything together. The horses move in perfect circles, supported by invisible arms, extending from a hidden center. This is much like what astronomers observed when they looked at galaxies: visible matter moving in perfect formation, guided by something they could not see. This invisible something came to be known as dark matter, though the name is somewhat misleading. It isn't necessarily dark in the way we usually think of darkness. Instead, it's transparent to light. Light passes right through it without interacting, making it completely invisible to our eyes and our instruments. It's like trying to see clear glass in perfectly clear water. As you lie here, feeling your body relax more deeply with each breath, consider this: dark matter particles might be flowing through you right now, billions upon billions of them, streaming silently through your body, through the earth, through everything you've ever known without leaving the slightest trace of their passage. Scientists estimate that in every cubic centimeter of space, a volume about the size of a sugar cube, there are thousands of dark matter particles drifting by every second. They pass through solid rock as easily as moonlight passes through mist. They are the universe's greatest magic trick, matter that has mass and gravity, but remains forever invisible, forever untouchable. The evidence for dark matter's existence comes not from seeing it directly, but from observing its gravitational effects on the things we can see. Like a detective investigating a crime scene, astronomers piece together clues left behind by this cosmic phantom. When they map the way galaxies move within galaxy clusters, those vast congregations of hundreds or thousands of galaxies bound together by gravity, they find that the visible stars and gas cannot account for the gravitational forces at work. There must be something else there, something with enormous mass, bending space and time itself to keep these cosmic cities from flying apart. It's a humbling realization. We who have named constellations and mapped the surfaces of distant planets find ourselves surrounded by a form of matter that we cannot see, cannot touch, cannot directly detect. It reminds us that the universe keeps its deepest secrets well hidden, revealing them only to those patient enough to listen to the subtle whispers of gravity and motion across cosmic distances. To understand the second great mystery, dark energy, we must first journey into one of the most beautiful and revolutionary ideas in all of science. The realization that space and time are not separate things, but are woven together into a single dynamic fabric that can stretch, bend, and curve. Imagine lying on a vast, soft mattress that extends infinitely in all directions. Now picture placing a bowling ball in the center of this mattress. The heavy ball creates a depression, causing the surface to curve around it. If you were to roll marbles across this curved surface, they would naturally follow the contours created by the bowling ball, spiraling around it in graceful arcs. This is much like how massive objects affect the fabric of space-time itself. The sun, with its enormous mass, creates a gentle depression in the space-time around it, and planets like Earth simply follow the natural curves of this cosmic geometry, orbiting not because they are being pulled by some invisible force, but because they are following the straightest possible path through curved space-time. Einstein revealed this elegant truth to us over a century ago. And as you rest here tonight, you can appreciate the poetry of it. You are not lying still on your bed. You are riding through space on a planet that is following the curves of space-time carved by our local star, traveling at incredible speeds through a universe that is itself in constant motion. But space-time holds another secret, one even more mysterious than dark matter. In the late 1990s, astronomers made a discovery that shook the foundations of cosmology. They were studying distant supernovae, massive stellar explosions, so bright they can be seen across billions of light years when they noticed something unexpected. These cosmic lighthouses revealed that the expansion of the universe, which began with the Big Bang nearly 14 billion years ago, is not slowing down as everyone expected. Instead, it's speeding up. Imagine blowing up a balloon, but instead of having to blow harder and harder to keep expanding it, you find that the balloon begins inflating faster and faster on its own, as if some invisible force were helping to stretch the rubber. This is what's happening to space itself. It's expanding at an accelerating rate, driven by something that astronomers have dubbed dark energy. Dark energy is even more mysterious than dark matter. While dark matter at least behaves like matter, it clumps together and creates gravitational effects we can measure. Dark energy appears to be a property of space itself. The more space expands, the more dark energy there is, and the more dark energy there is, the faster space expands. It's as if the very vacuum of space were alive with a subtle energy that grows stronger. As the universe grows larger, every cubic meter of empty space contributes a tiny push to the cosmic expansion. And when you add up all the empty space in the observable universe, this gentle push becomes the dominant force shaping the cosmos. As you continue to relax, let your imagination paint a picture of the universe on its largest scales. If you could step back far enough to see the entire cosmos at once, you would witness one of nature's most spectacular works of art, the cosmic web. Picture the most delicate spider's web you've ever seen, glistening with morning dew in a garden. Now imagine this web stretching not across a few inches of space, but across billions of light years. The filaments of this cosmic web are made not of silk, but of dark matter, creating invisible highways along which galaxies travel like glowing beads on cosmic string. At the intersections of these dark matter filaments, where multiple strands come together, we find the largest structures in the universe, galaxy clusters containing thousands of individual galaxies, all held together by the gravitational embrace of their dark matter scaffold. These cosmic cities are separated by vast voids, regions of space so empty that you might travel for hundreds of millions of light years without encountering a single galaxy. The cosmic web reveals the universe as an artist's masterpiece, painted on a canvas so large that light from its distant regions takes billions of years to reach us. When we look at galaxies far away, we see them as they were when the universe was young. Cosmic archaeology performed with telescopes, allowing us to witness the adolescence of creation itself. This grand structure grows and evolves over cosmic time, shaped by the invisible dance between dark matter and dark energy. Dark matter provides the gravitational framework, pulling ordinary matter together to form the first stars and galaxies. Meanwhile, dark energy works against this cosmic construction project, stretching space itself and trying to pull everything apart. For billions of years, dark matter held the advantage. Galaxies formed, stars were born, and the universe became a more structured and organized place. But as space expanded and dark energy grew stronger, the balance began to shift. Today, dark energy has become the dominant player in this cosmic drama, and its influence will only grow stronger with time. In the far distant future, perhaps trillions of years from now, dark energy will have stretched space so much that galaxies will become isolated islands, too far apart to see each other. The cosmic web will be stretched to its breaking point, leaving each galaxy to live out its final eons in cosmic solitude. But that future is unimaginably distant. For now, we live in a golden age of cosmic structure, when the universe is old enough to have created magnificent galaxies, and young enough that they can still communicate with each other across the vast expanses of space. As you drift closer to sleep, consider the remarkable human journey to understand these cosmic mysteries. Around the world, dedicated scientists work tirelessly to unveil the secrets of dark matter and dark energy, using some of the most sophisticated instruments ever created. Deep underground, in mines and laboratories, shielded from cosmic radiation, physicists build exquisitely sensitive detectors, hoping to catch the whisper of a dark matter particle as it passes through ordinary matter. These experiments require the patience of cosmic gardeners, waiting years for the slightest hint of interaction between the dark and visible worlds. In space, telescopes like the Hubble Space Telescope and the newer James Webb Space Telescope peer back through cosmic time, capturing light that has traveled for billions of years to reach us. Each photograph is a time machine, showing us the universe as it was when that light began its journey. By comparing images of the cosmos at different ages, astronomers can trace the evolution of dark energy's influence over cosmic history. On mountaintops around the Earth, arrays of radio telescopes listen to the cosmic background radiation, the afterglow of the Big Bang itself, searching for subtle patterns that might reveal how dark matter shaped the early universe. This ancient light carries within it the seeds of everything we see today, the blueprint for galaxies, stars, planets, and ultimately, life itself. Particle accelerators, those magnificent machines that push matter to nearly the speed of light, attempt to recreate the conditions that existed in the first moments after the Big Bang, hoping to produce dark matter particles in their high-energy collision. Each experiment is like a controlled explosion of pure energy, briefly recreating the primordial fire from which our universe emerged. Computer simulations run on supercomputers model the evolution of the cosmos over billions of years, testing our theories of dark matter and dark energy against the observed structure of the universe. These digital universes, containing billions of simulated particles, evolve according to the laws of physics, allowing scientists to experiment with different scenarios and see which ones most closely match reality. The search for understanding these cosmic mysteries represents humanity at its most noble and curious. We are a species that looks up at the night sky and asks not just what is out there, but how does it all work, and what is our place in this vast cosmic story. There's something profoundly moving about the realization that most of the universe remains hidden from us. In our daily lives, we often feel that we understand our world quite well. We can predict the weather, navigate by GPS, communicate instantly across vast distances. We have mapped the human genome and split the atom. We have walked on the moon and sent our robotic ambassadors to explore other planets. Yet when we step back and consider the cosmos as a whole, we discover that our knowledge barely scratches the surface of reality. The universe is far stranger and more mysterious than our ancestors ever imagined, filled with invisible matter and powered by an energy we cannot directly detect. This cosmic humility can be oddly comforting. It reminds us that we are part of something much larger than ourselves, something that transcends our everyday concerns and connects us to the deepest mysteries of existence. When we worry about small problems or get caught up in temporary difficulties, we can remember that we are made of star stuff, living on a tiny planet, in a galaxy containing hundreds of billions of stars, in a universe that may contain trillions of galaxies. The dark matter flowing through your body right now has traveled across cosmic distances, witnessing the birth and death of stars, the collision of galaxies, the expansion of space itself. You are intimately connected to the cosmos in ways both visible and invisible, both understood and mysterious. Dark energy, too, connects you to the largest scales of existence. The same force that is stretching the fabric of space-time between distant galaxies is present here, in this room, at this moment. Its effects are incredibly subtle on human scales. You will never feel dark energy directly, but it is part of the fundamental architecture of reality itself. In contemplating these mysteries, we join a conversation that stretches back to our earliest ancestors, who looked up at the same stars we see today and wondered about their nature and meaning. We are the universe becoming aware of itself, matter organized in such a way that it can contemplate its own existence and ask questions about its own origins and destiny. As you prepare for sleep, imagine yourself as an astronomer standing in an observatory on a clear, dark night. The Milky Way stretches across the sky above you like a river of light, containing perhaps 400 billion stars, each one a sun that might warm planets of its own. But now you know the secret. For every bit of ordinary matter you can see, every star, every planet, every glowing gas cloud, there is roughly 5 times as much dark matter surrounding it, supporting it, giving structure to the cosmic architecture. The visible universe is like foam on the ocean, beautiful and intricate, but floating on depths we can barely imagine. And beneath it all, or perhaps through it all, dark energy permeates every cubic centimeter of space, driving the grand expansion that began with the Big Bang and will continue long after our sun has burned out and our galaxy has aged beyond recognition. In this cosmic perspective, your worries and concerns take on a different character, not diminished for your life, and experiences are precious and real, but placed in a context so vast and magnificent that it can bring a sense of peace and wonder to even the most troubled mind. You are a temporary arrangement of atoms forged in the hearts of dying stars, given the remarkable gift of consciousness in a universe where dark matter flows silently through everything, and dark energy stretches the very fabric of reality. You are cosmic dust that learned how to dream, stellar debris that acquired the ability to wonder about its origins and contemplate its destiny. As you close your eyes and let sleep approach, feel yourself floating in this cosmic ocean. The dark matter streams around you like invisible currents, connecting you to every galaxy in the observable universe. Dark energy gently stretches the space between atoms, between molecules, between the thoughts in your mind, as it has been doing since the moment of creation. You are safe in this vast mystery, cradled by forces both seen and unseen, part of a story that began nearly 14 billion years ago and will continue for eons beyond imagination. The same laws of physics that govern the dance of galaxies also govern the beating of your heart and the firing of neurons in your brain as you drift towards sleep. Before you surrender completely to dreams, let your mind touch gently on the questions that these cosmic mysteries inspire. What is the true nature of dark matter? Is it made of particles unlike anything we've ever discovered? Could it be a sign that our understanding of gravity itself needs to be revised? And dark energy, is it truly a property of empty space itself? Or could it be something even more exotic? Might it be a field that permeates all of reality? Or could it be evidence that our universe exists within a larger multiverse, where different regions of space operate according to different physical laws? These questions do not demand immediate answers. They are like gentle waves lapping at the shore of human knowledge, reminding us that there is always more to discover, always deeper levels of mystery to explore. The universe is patient with our curiosity, revealing its secrets gradually, allowing each generation to contribute to our growing understanding of the cosmic story. Scientists of the future, perhaps some not yet born, will continue this great detective story, using technologies we cannot yet imagine to probe deeper into the nature of dark matter and dark energy. They may discover that these mysterious components are even stranger than we currently suppose, or they may find that the truth is elegant and simple, hiding in plain sight. But for now, in this quiet moment, it is enough to marvel at the mystery itself, to appreciate that we live in a universe far more wonderful and complex than our ancestors ever dreamed, to feel a sense of awe at the realization that invisible rivers of dark matter flow through our galaxy, and that the expansion of space itself is accelerating under the influence of a force we barely comprehend. As consciousness begins to fade and dreams approach, let yourself drift on these cosmic currents. Feel the gentle pull of dark matter's gravity. Sense the subtle push of dark energy expanding the space around you. You are part of the universe's greatest mystery, and the universe is part of you. The stars that shone on the first humans to wonder about the cosmos shine on you tonight. The same dark matter that helps hold our galaxy together flows through your sleeping form. The same dark energy that will determine the ultimate fate of everything connects you to the deepest levels of physical reality. Rest well, cosmic dreamer. Let the mysteries of dark matter and dark energy carry you gently into sleep, knowing that you are home in this vast, strange, beautiful universe, wrapped in forces both visible and invisible, part of a story so magnificent that consciousness itself emerged to contemplate it. The universe dreams through you, and tonight, you dream with the universe. Now we journey into the realm of the invisible sculptor, a mysterious presence that has shaped every galaxy, every cluster of stars, every vast structure in our universe, yet remains completely hidden from our sight. Imagine drifting peacefully through space, weightless and serene, as we explore the gentle influence of dark matter. This invisible hand has been guiding the cosmic dance for nearly 14 billion years, working silently behind the scenes to create the magnificent universe we call home. As you settle into comfort, allow yourself to become one with this cosmic story, where the greatest architecture in existence has been built by forces we cannot see. Dark matter is the universe's master architect, patient, persistent, and impossibly subtle. It works not with stone or steel, but with the fundamental fabric of space-time itself, using gravity as its tool to sculpt galaxies from primordial chaos. Every breath you take carries atoms that have been arranged by dark matter's influence. Every star you've ever seen owes its existence to structures built by this cosmic phantom. Tonight, as sleep approaches like a gentle tide, let us explore how scientists discovered this invisible realm and what it means for our understanding of everything that exists. We'll journey through the evidence that reveal dark matter's presence, meet the mysterious particles that might comprise it, and witness how it continues to shape the cosmos on scales both vast and intimate. Allow the mystery to embrace you like a warm blanket as we begin this peaceful exploration of the universe's hidden architecture. Our story begins in the 1930s, with a quiet astronomer named Fritz Zwicky, who was studying the Coma Cluster, a collection of over 1,000 galaxies bound together in a cosmic embrace. As you lie here relaxing, imagine Zwicky hunched over his telescope on a clear mountain night, meticulously measuring the velocities of these distant island universes. What he discovered was deeply puzzling. The galaxies in the cluster were moving far too quickly for the gravity of their visible matter to hold them together. According to the mathematics, they should have been flung apart eons ago, scattered across the cosmos like leaves in a cosmic wind. Yet there they were, serenely dancing together in their gravitational ballet, as if held by invisible threads. Zwicky proposed that some form of missing mass must be present, matter that could not be seen but whose gravitational influence was undeniable. He called it dark matter, a name that would echo through the decades as more and more evidence accumulated for this cosmic phantom. But it was not until the 1970s that the case for dark matter became truly compelling. A dedicated astronomer named Vera Rubin began a systematic study of spiral galaxies, measuring how fast stars orbit around their galactic centers. Her work would revolutionize our understanding of the cosmos and reveal the true extent of dark matter's influence. Picture our own Milky Way galaxy as you drift towards sleep, a magnificent spiral of 400 billion stars, each following its own orbital path around the galactic center. In our solar system, the planets follow a predictable pattern. Mercury races around the Sun in just 88 days, while distant Neptune takes 65 years to complete a single orbit. The farther from the Sun, the slower the orbital speed. Rubin expected to find the same pattern in galaxies, stars near the center orbiting quickly, while those on the outer edges moved more sedately through space. Instead, she discovered something extraordinary. Stars throughout the galaxy, from center to edge, maintained roughly the same orbital speed. It was as if the entire galaxy were rotating like a solid disk rather than following the laws of gravitational dynamics. The only way to explain this unexpected rotation pattern was to invoke vast amounts of invisible matter, dark matter, distributed throughout each galaxy like an enormous unseen halo. This dark matter halo extends far beyond the visible stars, creating a gravitational framework that keeps the galaxy's rotation uniform and stable. As you breathe slowly and deeply, imagine yourself floating within our galaxy's dark matter halo. Trillions upon trillions of mysterious particles stream around you, creating the invisible architecture that holds our cosmic home together. They pass through your body without interaction, yet their collective gravitational embrace encompasses every star you see in the night sky. The evidence for dark matter extends far beyond galactic rotation curves. One of the most beautiful confirmations comes from a phenomenon that transforms the cosmos into a vast optical instrument: gravitational lensing. As you settle deeper into relaxation, let your mind journey to where space and time bend around massive objects, creating cosmic magnifying glasses of extraordinary power. Einstein revealed to us that massive objects warp the fabric of space-time itself, much like a heavy ball creates a depression in a stretched rubber sheet. When light from distant galaxies travels through these warped regions, its path bends and curves, following the contours of curved space-time like water flowing around a stone. This cosmic lensing allows astronomers to map the distribution of dark matter with remarkable precision. Even though dark matter remains invisible, its gravitational influence on light reveals its presence like footprints in cosmic snow. Galaxy clusters act as enormous lenses, magnifying and distorting the images of galaxies that lie far behind them. In some cases, gravitational lensing creates multiple images of the same distant galaxy, stretched into graceful arcs and rings around the lensing cluster. These cosmic mirages are among the most beautiful sights in astronomy. Delicate blue crescents and golden rings painted across the darkness, each one a testament to dark matter's invisible presence. The most dramatic evidence came from observations of colliding galaxy clusters, cosmic car crashes that unfold over millions of years. When two massive clusters collide, their ordinary matter, hot gas and plasma interact violently, creating shock waves and friction that slow the collision. But dark matter, which interacts only through gravity, passes through the collision largely unaffected. The result is a cosmic forensic scene where dark matter and ordinary matter become separated, allowing astronomers to map their distributions independently. These observations provide direct visual evidence that dark matter exists as something distinct from ordinary matter, behaving according to its own mysterious rules. One such collision, known as the bullet cluster, shows dark matter racing ahead of the ordinary matter, like a ghost passing through a wall. The dark matter's gravitational lensing effects are clearly visible, offset from the hot gas revealed by X-ray telescopes. It's a smoking gun for dark matter's existence, proof that the universe contains vast amounts of matter that interacts with ordinary matter only through the gentle pull of gravity. As you drift closer to sleep, imagine these cosmic collisions happening in slow motion across millions of years, dark matter flowing like invisible rivers through the chaos, maintaining its ethereal integrity, while ordinary matter crashes and burns in spectacular displays of cosmic violence. What could dark matter actually be? This question has captivated physicists for decades, leading them to imagine new types of particles that exist beyond our current understanding of matter and energy. As you rest here peacefully, let your mind explore the menagerie of theoretical particles that might comprise the universe's dark sector. The leading candidates are particles with wonderfully evocative names, WIMPs or weakly interacting massive particles. These hypothetical particles would be similar to neutrinos, ghostly particles that stream through ordinary matter as if it weren't there, but much more massive. A WIMP might weigh as much as a heavy atomic nucleus, yet interact so weakly with ordinary matter that trillions could pass through your body every second without leaving a trace. Imagine WIMPs as cosmic raindrops falling silently through everything in existence. They would pass through planets, stars and entire galaxies, with barely any interaction, their presence revealed only through their gravitational effects on the large-scale structure of the universe. These particles might have been created in the first moments after the Big Bang, when the universe was a hot, dense soup of energy and exotic matter. Another intriguing possibility is the axion, a particle so delicate and elusive that it makes WIMPs seem robust by comparison. Axions would be incredibly light, perhaps 1 trillion times lighter than an electron, and would interact with ordinary matter even more weakly than WIMPs. Yet their sheer numbers could make up a significant fraction of the universe's dark matter. Picture axions as an invisible ocean pervading all of space. With individual particles so light, they behave more like waves than discrete objects. This cosmic ocean would be in constant motion, flowing and oscillating in patterns too subtle for our current instruments to detect. The entire universe might be filled with axion waves, creating a background hum in the quantum vacuum that we have yet to learn how to hear. Some theories propose even more exotic possibilities. Sterile neutrinos, hypothetical cousins of ordinary neutrinos that interact even more weakly with matter, might comprise dark, or perhaps dark matter consists of primordial black holes, microscopic remnants from the universe's earliest moments that have been quietly influencing cosmic evolution for billions of years. There might even be an entire dark sector of physics, with dark matter particles that interact with each other through their own set of forces, invisible to us but creating rich structures and dynamics in the hidden universe. Dark atoms, dark molecules, even dark chemistry might be unfolding all around us. A parallel reality that shares our space but remains forever separate from our direct experience. As you breathe slowly and steadily, consider that your body might be host to countless dark matter particles at this very moment. They flow through your cells, through your DNA, through the electrical signals in your brain, without disturbing a single atom. You are immersed in an ocean of invisible matter, yet it touches you more gently than the softest breeze. To understand dark matter's true significance, we must journey to the largest scales of existence, where its influence becomes most apparent. In the peaceful darkness behind your closed eyes, envision the universe as it appears, when viewed from the greatest possible distance, a magnificent web of light and shadow stretching across billions of light years. This cosmic web is dark matter's greatest masterpiece. In the universe's infancy, when it was less than 400,000 years old, dark matter began clumping together under its own gravity, creating the first structures in the cosmos. These dark matter clumps grew slowly over millions of years, their gravitational pull eventually becoming strong enough to attract ordinary matter and begin the process of star formation. Imagine the young universe as a vast, gently rolling landscape of dark matter hills and valleys. Ordinary matter, hydrogen, and helium gas flowed like water into the deepest valleys, pooling in the gravitational wells created by dark matter's invisible architecture. As this gas accumulated and compressed, it eventually became dense and hot enough to ignite the first stars. These primordial stars were cosmic lighthouses, illuminating a universe that had been dark for millions of years. But they were only able to form because dark matter had already built the gravitational scaffolding necessary to collect and concentrate the raw materials for starbirth. Every star that has ever shone, including our own sun, owes its existence to structures originally laid down by dark matter. As eons passed, dark matter continued to sculpt the cosmic landscape. Small clumps merged to form larger ones, which in turn combined to create the massive dark matter halos that now surround every galaxy. These halos extend far beyond the visible boundaries of their galaxies, creating invisible spheres of influence that can be hundreds of times larger than the bright stellar disks we see through telescopes. The cosmic web that emerged from this process resembles the neural networks in a vast cosmic brain. Filaments of dark matter stretch across hundreds of millions of light years, connecting galaxy clusters like synapses in an unimaginably large mind. At the intersections of these filaments, where multiple streams of dark matter converge, we find the largest structures in the universe. Massive galaxy clusters containing thousands of individual galaxies, all bound together by dark matter's gravitational embrace. Between these filaments lie the cosmic voids, vast regions of space, so empty that a traveler might journey for hundreds of millions of light years without encountering a single galaxy. These voids are not truly empty, but they contain so little dark matter that ordinary matter has had little opportunity to accumulate and form stars. As you drift towards sleep, imagine yourself traveling along one of these dark matter filaments, following an invisible highway that connects distant galaxy clusters. The journey would take hundreds of millions of years at the speed of light, yet you would be traveling along structures laid down by dark matter when the universe was young. You are following ancient pathways built by the cosmos itself, guided by forces that remain forever hidden from direct observation. The relationship between dark matter and ordinary matter is like a cosmic symphony, with dark matter providing the underlying rhythm that allows the melody of stars and galaxies to emerge. As you rest here in peaceful contemplation, let your mind appreciate the subtle harmony between the visible and invisible components of our universe. Without dark matter's patient work over cosmic time, the universe would be a very different place. Computer simulations that attempt to model cosmic evolution without dark matter produce universes that are smooth and featureless, endless expanses of gas that never clump together sufficiently to form stars or galaxies. It is dark matter's gravitational scaffolding that makes possible all the complex structures we see in the night sky. Dark matter halos act as cosmic nurseries, providing the stable gravitational environment necessary for galaxy formation. Within these invisible cradles, ordinary matter can accumulate gradually, forming the rotating disks of gas that eventually give birth to stellar generation. The spiral arms of galaxies, those graceful curves that make them so beautiful in photographs, are pressure waves traveling through the galactic disk, waves that can only exist because dark matter provides the gravitational foundation that keeps the disk stable over billions of years. Even the formation of planets like Earth depends ultimately on dark matter's influence. The heavy elements necessary for rocky planet formation, carbon, oxygen, silicon, iron, were forged in the nuclear furnaces of massive stars. These stars could only form because dark matter had already created the gravitational wells where gas could accumulate and ignite. The calcium in your bones, the iron in your blood, the carbon in your DNA, all of these elements trace their origins back to dark matter's patient construction work in the early universe. The influence extends to the smallest scales as dark matter particles streaming through our solar system create tiny perturbations in the orbits of planets and spacecraft. These effects are incredibly subtle, far too small to affect daily life, but sensitive enough that future space missions might use them to map the local dark matter environment. Our galaxy's dark matter halo creates a gentle background influence that affects everything within it. The halo's rotation helps determine the overall motion of our solar system through space, while its gravitational field shapes the paths of comets in the outer reaches of our solar system. We are quite literally embedded within dark matter's embrace, carried along by its ancient currents like leaves floating on an invisible cosmic river. As you breathe slowly and rhythmically, feel yourself moving through space at tremendous speed, not just spinning with Earth's rotation or orbiting the Sun, but traveling with our entire solar system as it orbits the galactic center, guided by dark matter's gravitational influence. You are on a cosmic journey that began billions of years ago and will continue long after human civilization has faded into cosmic history. Around the world, scientists conduct one of the most ambitious treasure hunts in history, the search for direct evidence of dark matter particles. Their quest takes them to the deepest laboratories on Earth and the furthest reaches of space, using instruments of extraordinary sensitivity to catch the faintest whisper of interaction between the dark and visible worlds. Deep beneath mountains and in abandoned mines, physicists have built cathedrals of detection, vast underground chambers filled with tanks of liquid xenon, crystals of silicon and germanium, and other exotic materials chosen for their ability to record the slightest disturbance. These detectors are kept at temperatures colder than outer space and shielded by thousands of feet of rock from cosmic radiation that might interfere with their delicate measurements. The principle is beautifully simple. If dark matter particles occasionally interact with ordinary matter, even incredibly rarely, then a sensitive enough detector should eventually record such an interaction. Scientists wait with cosmic patience for a dark matter particle to collide with an atomic nucleus in their detector, creating a tiny flash of light or a microscopic vibration that reveals the presence of this invisible visitor. Imagine these underground laboratories as monasteries of science, where researchers maintain vigils lasting years or decades, watching for signals so subtle they must distinguish them from the natural radioactivity of rocks, the vibrations of distant traffic, even the slight gravitational effects of the moon's orbit. It is a meditation on the limits of detection, pushing human technology to its absolute boundaries in pursuit of the universe's deepest secret. Other experiments take a different approach, using particle accelerators to recreate the conditions that existed shortly after the Big Bang, when dark matter particles might have been produced in abundance. These cosmic fireworks attempt to reverse engineer dark matter creation, colliding ordinary particles at enormous energies to see if they can produce new types of matter that quickly decay or disappear, signs that dark matter particles have been briefly brought into existence. Space-based detectors orbit high above Earth's atmosphere, looking for the products of dark matter annihilation, the light and particles that might be produced when two dark matter particles collide and destroy each other. These cosmic ray detectors scan the heavens for subtle signals that might reveal dark matter's presence in the center of our galaxy, where theory predicts the highest concentrations should exist. Radio telescopes listen for the whispers of axions, which theory suggests might convert into detectable radio waves when passing through strong magnetic fields. These experiments probe frequency ranges with names like axion windows, searching for signals so faint they would be completely overwhelmed by the background noise of human civilization, if not for the most sophisticated filtering techniques ever developed. As you drift towards sleep, appreciate the dedication of these cosmic detectives, spending their careers in pursuit of particles that may interact with ordinary matter only once in a billion collisions. Their patient vigil is a testament to human curiosity and our deep desire to understand the hidden architecture of reality. At the deepest level, dark matter represents a profound mystery about the quantum nature of reality itself. As you settle into the peaceful rhythm of approaching sleep, let your mind contemplate the quantum dance that might be unfolding in the space around you. Invisible choreography performed by particles that exist at the very edge of the possible. In the quantum realm, particles can exist in multiple states simultaneously, tunnel through barriers that should be impenetrable, and remain connected across vast distances through mysterious quantum entanglement. Dark matter particles, if they exist, must navigate this strange quantum landscape while somehow maintaining their classical gravitational effects on the large-scale structure of the universe. Some theories suggest that dark matter particles might exist in a quantum superposition, simultaneously present and absent, until some interaction causes their quantum wave function to collapse into a definite state. Others propose that dark matter might be composed of quantum fields that permeate all of space, with particle-like excitations appearing only under special circumstances. The mathematics describing dark matter candidates often involves dimensions beyond the familiar three of space and one of time. In these higher dimensional theories, dark matter particles might be ordinary particles that have become trapped in extra dimensions we cannot perceive, able to interact with our three-dimensional world only through the universal language of gravity. Imagine dark matter as shadows cast by objects moving through higher dimensions, two-dimensional shadows on a three-dimensional wall that give hints about the true nature of the objects casting them. We see only the gravitational shadows of dark matter, projected into our familiar space-time from realms that exist beyond our direct perception. String theory, which attempts to unify all the forces of nature, predicts a rich spectrum of possible dark matter candidates. In this framework, the fundamental constituents of reality are not point-like particles, but tiny vibrating strings, and dark matter might consist of string excitations that interact only weakly with the string modes we recognize as ordinary matter. These theories paint a picture of reality that is far richer and more complex than our everyday experience suggests. We might be living in a universe where most of matter exists in forms we cannot directly perceive, following quantum mechanical rules that allow for possibilities we can barely imagine. As your breathing slows and consciousness begins to fade, consider that you might be surrounded by quantum fields of dark matter, their wave functions gently oscillating through the space between atoms, creating probability clouds of invisible matter that extend throughout your body and beyond. You are part of a quantum cosmos where the boundary between the possible and actual is far more fluid than classical physics suggests. As you prepare to surrender to sleep, let your final thoughts drift to the eternal nature of dark matter's influence. This invisible architect has been shaping the cosmos since the universe's earliest moments, and will continue its patient work long after stars have burned out and galaxies have aged beyond recognition. In the far future, when the last red dwarf stars have exhausted their nuclear fuel and black holes dominate the cosmic landscape, dark matter will still be there, maintaining its gravitational vigil over a universe grown cold and dark. The dark matter halos that now cradle galaxies will persist as gravitational fossils, marking where vibrant stellar communities once flourished. Even as the universe expands and dark energy stretches space to unimaginable scales, dark matter will continue to hold together the largest bound structures, creating islands of gravitational stability in an ocean of cosmic expansion. These dark matter strongholds will be among the last bastions of structure in a universe gradually succumbing to entropy and isolation. Yet dark matter's greatest legacy may be the role it played in making possible the emergence of complexity, structure, and ultimately consciousness itself. Without dark matter's patient construction work in the early universe, there would have been no galaxies, no stars, no planets, no chemistry complex enough to give rise to life. You exist because dark matter built the cosmic architecture necessary for star formation, element creation, and planetary systems. The thoughts flowing through your mind as you drift towards sleep are made possible by the invisible scaffolding that dark matter erected billions of years ago. You are a temporary pattern of consciousness arising from matter that was organized by forces you cannot see, cannot touch, cannot directly detect. In this sense, dark matter is not separate from you, but intimately connected to your existence. The invisible threads that hold galaxies together also weave through the story of your own being. You are dark matter's grandchild, a brief flowering of awareness in a cosmos shaped by invisible hands. As sleep takes hold, feel yourself dissolving into the cosmic web, becoming one with the dark matter streams that flow through our galaxy. Your consciousness merges with the universal field of gravitational influence that connects every star, every planet, every atom in existence. You are part of the eternal architecture, a temporary focusing of cosmic awareness that arose from the patient work of invisible builders. Imagine the universe as a vast balloon, expanding not into space but as space itself, carrying galaxies like specks of dust on its surface. For nearly 14 billion years, this cosmic balloon has been inflating, and for most of that time, astronomers believed this expansion was gradually slowing down, like a ball thrown upward eventually succumbing to gravity's pull. But in the late 1990s, a discovery shook the foundations of cosmology. The universe's expansion wasn't slowing down, it was speeding up. Something was pushing against gravity itself, stretching the fabric of space-time with ever-increasing vigor. This mysterious force came to be known as dark energy, though it is neither dark in the usual sense nor energy as we commonly understand it. As you settle into the peaceful rhythm of approaching sleep, let your mind drift through this cosmic mystery. Dark energy comprises roughly 70% of everything that exists, yet it remains more enigmatic than dark matter, more puzzling than black holes, more mysterious than the quantum foam that bubbles at the smallest scales of reality. Tonight, we'll follow the trail of discovery that revealed this cosmic accelerator, explore the theories that attempt to explain its nature, and journey to the cutting edge of research, where scientists work tirelessly to understand the force that will determine the ultimate fate of our universe. Allow yourself to float on the cosmic expansion itself, carried by the gentle current of dark energy toward the deepest mysteries of existence. Our story begins with stellar explosions so violent they can outshine entire galaxies. Supernovae, the dramatic death throes of massive stars. As you rest here peacefully, imagine these cosmic lighthouses scattered across the universe, each one a cosmic yardstick that allows astronomers to measure distances across billions of light years. In the 1990s, two independent teams of astronomers set out to use a special type of supernova, type Ia supernovae, to measure the expansion rate of the universe with unprecedented precision. These stellar explosions are remarkably consistent in their brightness, earning them the nickname standard candles. By comparing their apparent brightness to their known intrinsic luminosity, astronomers can calculate exactly how far away they are. The teams led by Saul Perlmutter, Brian Schmidt, and Adam Rees expected to find that the universe's expansion was gradually slowing down. After all, gravity should be pulling everything back together, fighting against the initial impulse of the Big Bang. They thought they would measure exactly how much this cosmic deceleration was occurring. Picture these dedicated astronomers, spending clear nights on mountaintops around the world, their telescopes trained on distant galaxies, patiently waiting for the brief flash of a supernova to appear. Each explosion they detected was a messenger from the ancient past, its light having traveled for billions of years to reach their instruments. They were cosmic archaeologists, using stellar explosions to probe the expansion history of the universe itself. What they discovered was completely unexpected. The distant supernovae appeared dimmer than they should have if the universe's expansion was slowing down. Instead, they appeared exactly as dim as they would if the expansion were accelerating, as if some invisible force were pushing space itself apart with ever-increasing strength. At first, the astronomers checked and rechecked their calculations, suspecting some systematic error in their observations. The implications were too profound to accept without overwhelming evidence. But as more data accumulated, the conclusion became inescapable. The universe's expansion was indeed accelerating, driven by something that had never been directly observed. This discovery earned the three team leaders the 2011 Nobel Prize in Physics and revolutionized our understanding of the cosmos. It revealed that we live in a universe dominated by a mysterious form of energy that acts like gravity turned inside out. Instead of pulling things together, it pushes them apart. As you breathe slowly and rhythmically, imagine yourself floating in this expanding universe, feeling the gentle stretch of space itself, carrying you along. The distance between you and every distant galaxy is growing, not because anything is moving through space, but because space itself is expanding, inflated by the mysterious pressure of dark energy. To understand dark energy, we must first appreciate the revolutionary idea that space and time are not fixed background against which events unfold, but are themselves dynamic entities that can stretch, bend, and evolve. As you drift deeper into relaxation, let your mind journey into Einstein's elegant vision of space-time as a living, breathing fabric. Imagine space-time as an infinite ocean, its surface rippling with gravitational waves, its depths curved by the presence of matter and energy. In this cosmic ocean, planets and stars are like floating objects, following the natural currents and eddies created by mass and energy. But the ocean itself is not static. It's expanding, carrying everything along with it, like debris floating on a rising tide. Einstein's equations, formulated over a century ago, describe how matter and energy curve space-time, and how curved space-time tells matter how to move. But these same equations contain a mysterious term, the cosmological constant, that Einstein originally introduced to allow for a static universe. He later called it his greatest blunder, when observations revealed that the universe was expanding. Ironically, this discarded cosmological constant has returned as the leading candidate to explain dark energy. In this interpretation, empty space itself possesses a fundamental energy density, a quantum foam of virtual particles constantly appearing and disappearing, creating a subtle but persistent pressure that pushes space apart. Think of it as the universe having a built-in restlessness, an intrinsic tendency to expand written into the very laws of physics. Every cubic meter of empty space contributes the same tiny amount of expansive pressure, and as the universe grows larger, there's more empty space, which means more total dark energy, which drives even faster expansion. This creates a feedback loop that will ultimately dominate the cosmic future. Unlike matter and radiation, which become diluted as space expands, dark energy maintains constant density. As the universe doubles in size, the amount of matter and radiation stays the same, but the amount of dark energy doubles. One of the most profound aspects of the dark energy mystery lies in the quantum nature of empty space itself. As you rest here in the quiet darkness, let your mind explore the possibility that nothingness is actually filled with invisible activity, a quantum foam of energy that might be the source of the universe's accelerating expansion. According to quantum mechanics, even empty space is never truly empty. The uncertainty principle, one of the fundamental laws of quantum physics, tells us that energy can spontaneously appear and disappear on incredibly short timescales. Virtual particles, pairs of matter and antimatter, constantly pop into existence and annihilate each other in the space around you, creating a background sea of quantum fluctuation. This quantum vacuum energy should, in principle, act like dark energy, creating a pressure that drives cosmic expansion. But when physicists calculate how much vacuum energy there should be, they get a number that's larger than the observed dark energy density by a factor of 10. This is perhaps the worst theoretical prediction in the history of science, a discrepancy so enormous it boggles the mind. This failure suggests that our understanding of either quantum mechanics or general relativity, or both, is incomplete in some fundamental way. The vacuum energy problem points to new physics lurking just beyond our current theoretical reach, possibly involving extra dimensions, modifications to gravity, or entirely new principles we haven't yet discovered. Yet the quantum vacuum remains tantalizingly connected to dark energy through the cosmological constant. Einstein's equations naturally accommodate a constant energy density throughout space, and if this energy density is small enough, it could explain the observed acceleration without conflicting with other observations. The mystery is why this constant should have exactly the value needed to become important now, after billions of years of cosmic evolution. Some physicists propose that the cosmological constant might be determined by the landscape of possible universes in string theory. In this multiverse scenario, different regions of a higher dimensional space might have different values of the cosmological constant, and we find ourselves in a region where its value allows for the formation of stars, galaxies, and ultimately life itself. This anthropic reasoning suggests that the cosmological constant might not be calculable from first principles, but instead represents a kind of cosmic lottery ticket. We live in a universe with the right value simply because universes with vastly different values couldn't support the complex chemistry necessary for observers like us exist. As you breathe slowly and deeply, imagine the quantum foam bubbling silently in the space around you, virtual particles dancing their brief existence before vanishing back into the vacuum. This microscopic choreography might be connected to the grandest scales of cosmic evolution, linking the smallest fluctuations in spacetime to the ultimate fate of the universe itself. Not all theories of dark energy invoke Einstein's cosmological constant. An alternative class of models known as quintessence proposes that dark energy might be a dynamic field that evolves over cosmic time, like a cosmic fluid slowly changing its properties as the universe ages. The name quintessence comes from ancient Greek philosophy, referring to the fifth element that was thought to fill the celestial spheres beyond the earthly realm of fire, water, air. In modern cosmology, quintessence fields represent a similarly ethereal component that permeates all of space, while remaining largely invisible to ordinary matter. Unlike the cosmological constant which never changes, quintessence fields can evolve, potentially solving some of the puzzles associated with dark energy. For instance, a quintessence field might naturally become important at the present epoch, explaining why dark energy's effects are becoming noticeable now, rather than in the early universe when matter and radiation dominate. Imagine quintessence as a cosmic weather system with pressure patterns and flows that vary across space and time. Just as atmospheric pressure changes can drive weather on Earth, variations in the quintessence field might create subtle variations in the rate of cosmic expansion, potentially leaving detectable signatures in the cosmic microwave background radiation, or the distribution of galaxies. Some quintessence models predict that dark energy's influence might actually decrease in the future, potentially allowing gravity to halt the cosmic acceleration and even reverse it. In these scenarios, the universe might eventually stop expanding and begin contracting in a big crunch, the opposite of the Big Bang that would bring all matter back together in a final cosmic collision. Other quintessence models suggest that dark energy might grow stronger over time, leading to an eventual big rip where the expansion becomes so violent that it tears apart galaxies, stars, planets, and ultimately even atoms themselves. In this scenario, the fundamental forces holding matter together would be overcome by the relentless expansion of space. The mathematics of quintessence involves scalar fields, quantities that have a value at every point in space, but don't point in any particular direction. Unlike the familiar vector fields of electromagnetism, these scalar fields can have potential energy functions that determine how they evolve over time, much like a ball rolling down a hill follows the shape of the landscape. The beauty of quintessence models is that they connect dark energy to the same mathematical framework used to describe the inflationary period that may have occurred just after the Big Bang. In both cases, scalar fields with special properties drive periods of accelerated expansion, suggesting that cosmic acceleration might be a recurring theme in the universe's history. As you drift towards sleep, imagine yourself floating in a cosmic ocean of quintessence, feeling the subtle currents and tides of this invisible field as it slowly evolves across cosmic time. You are immersed in the very force that will determine the ultimate fate of everything that exists, yet it touches you more gently than the softest whisper. Around the world, scientists are conducting some of the most ambitious experiments in human history to unravel the mystery of dark energy. Their efforts span from ground-based telescopes to space missions, from underground laboratories to supercomputer simulations, all aimed at understanding the force that dominates our cosmic destiny. One of the most powerful approaches involves mapping the positions and distances of millions of galaxies to create three-dimensional maps of cosmic structure. These galaxy surveys reveal how the universe's web-like structure has evolved over billions of years, carrying the imprint of dark energy's influence on the growth of cosmic architecture. The Dark Energy Survey, conducted using a specially designed camera on a telescope in Chile, has mapped over 300 million galaxies across 1/8 of the entire sky. Each galaxy's position and distance tells part of the story of cosmic evolution, and together they create a fossil record of how dark energy has shaped the universe's structure over cosmic time. Picture astronomers spending clear nights in the Atacama Desert, one of the driest places on Earth, their telescope automatically photographing galaxy after galaxy, building a cosmic census of unprecedented scope and precision. Each image captures light that has traveled for billions of years, carrying information about the state of the universe when that light first began its journey. Space-based missions, like the European Space Agency's Euclid satellite, take this mapping to even greater precision, observing billions of galaxies from above Earth's atmosphere, free from atmospheric distortion. These space telescopes can measure the subtle distortions in galaxy shapes caused by gravitational lensing, revealing how dark matter and dark energy have sculpted the cosmic web. Other experiments focus on supernovae, the cosmic explosions that first revealed dark energy's existence. Modern supernova surveys can detect these stellar explosions across vast distances and times, building up detailed records of how the universe's expansion rate has changed throughout cosmic history. The Large Synoptic Survey Telescope, now known as the Vera Rubin Observatory, will revolutionize this field by discovering thousands of supernovae every night, building up statistical samples large enough to detect subtle variations in dark energy's behavior over cosmic time. Each supernova becomes a data point in humanity's growing understanding of cosmic acceleration. Laboratory experiments also contribute to the dark energy puzzle. Searches for axions, hypothetical particles that might comprise dark matter, could also reveal new physics relevant to dark energy. Underground detectors, sensitive to gravitational waves, might detect signals from cosmic strings or other exotic objects that could shed light on the nature of space itself. Computer simulations running on the world's most powerful supercomputers model the evolution of the universe under different assumptions about dark energy, testing which theories match the observed distribution of galaxies and cosmic structure. These digital universes evolve over billions of simulated years, allowing scientists to explore cosmic scenarios that would take longer than the age of the universe to observe directly. As you settle into deeper relaxation, appreciate the dedication of these cosmic explorers, spending their careers pushing the boundaries of human knowledge into realms that dwarf our everyday experience. They are mapping the invisible architecture of reality itself, using the entire observable universe as their laboratory. Some of the most speculative theories about dark energy connected to the possibility that our universe might be just one bubble in an infinite cosmic foam, a multiverse where different regions of space operate according to different physical laws and constants. In this grand vision, the value of dark energy in our universe might not be determined by fundamental physics, but might instead represent a kind of cosmic accident, one possibility among an infinite number of alternatives. String theory, which attempts to unify all the forces of nature, suggests that there might be an enormous number of possible vacuum states, each with its own value of the cosmological constant. Imagine a vast landscape of possible universes, each peak and valley representing a different combination of physical constants and laws. Our universe sits in one particular valley, where the dark energy density happens to have a value that allows for the formation of stars, galaxies, and complex chemistry. Other valleys might have values so large that cosmic acceleration prevents any structure from forming, or so negative that the universe quickly collapses back on itself. This multiverse perspective offers a potential solution to the coincidence problem, the puzzle of why dark energy became important at roughly the same time that intelligent life evolved in the universe. If there are countless universes with different dark energy values, then we naturally find ourselves in one where the value is compatible with our existence. The anthropic principle suggests that many seemingly fine-tuned aspects of our universe might actually be explained by selection effects rather than fundamental physics. Just as we find ourselves on a planet with liquid water and a suitable atmosphere because planets without these properties can't support life, we might find ourselves in a universe with suitable dark energy because universes with unsuitable values can't support observe. Yet this raises profound questions about the nature of explanation in science. If the properties of our universe are determined by a cosmic lottery rather than fundamental principles, then some aspects of reality might forever remain beyond the reach of traditional scientific inquiry. We might be able to map and measure dark energy's effects, but never truly understand why it has the value it does. Other multiverse scenarios suggest more dynamic possibility. In eternal inflation models, new universes might constantly be budding off from existing ones, each inheriting slightly different physical property. Dark energy might represent the continuing influence of this cosmic reproduction process, connecting our local universe to a vast network of cosmic evolution. Some theories propose that universes might even be able to influence each other across the multiverse landscape, potentially explaining dark energy as a kind of gravitational leak from neighboring universes. In this scenario, the force driving cosmic acceleration might not originate within our universe at all, but might seep in from parallel realities we can never directly observe. As you drift closer to sleep, imagine yourself floating not just in our universe, but in the vast multiverse ocean, with countless other realities extending in dimensions beyond space and time. Your consciousness briefly flickers in one small corner of infinite possibility, temporarily focusing cosmic awareness in a universe where dark energy happens to have just the right value to allow for the emergence of wonder and contemplation. The ultimate fate of our universe depends critically on the true nature of dark energy, making this abstract scientific puzzle one of the most practically important questions in all of human inquiry. As you rest here peacefully, let your mind journey to the far future, where dark energy's influence will determine the final chapter of the cosmic story. If dark energy is truly a cosmological constant, never changing throughout cosmic time, then our universe faces a future of eternal expansion and gradual cooling. Galaxies will drift apart until they can no longer see each other, isolated islands of matter in an ever-expanding sea of space. Stars will eventually exhaust their nuclear fuel, leaving behind white dwarfs, neutron stars, and black holes in a universe grown cold and dark. Even the black holes will eventually evaporate through Hawking radiation, leaving behind a thin soup of elementary particles drifting through space at temperatures approaching absolute zero. This heat-death scenario represents the ultimate triumph of entropy over order, with dark energy continuing to stretch space long after every organized structure has dissolved. But if dark energy is quintessence, a dynamic field capable of changing over time, then other possibilities emerge. The field might decay or transition to a different state, potentially reducing the cosmic acceleration or even reversing it entirely. Universe might enter a new phase of evolution, with possibilities we can barely imagine. Some quintessence models predict a Big Rip scenario, where dark energy grows stronger over time, eventually becoming so powerful that it overcomes all other forces in nature. In this dramatic ending, cosmic expansion would become so violent that it tears apart galaxies, then solar systems, then planets, then molecules, and finally even atomic nuclei, reducing all matter to its most fundamental constituent. The timeline for such a cosmic catastrophe would be tens of billions of years in the future, vastly longer than the current age of the universe. During this enormous span of time, countless generations of stars could be born and die, entire civilizations could rise and fall, and evolution could explore possibilities we cannot begin to fathom. Other scenarios involve cyclic cosmologies, where the universe periodically expands and contracts in an eternal rhythm of cosmic breathing. Dark energy might be just one phase in an infinite cycle of expansion and collapse, with each cycle potentially giving birth to new physical laws and new possibilities for matter and energy. Perhaps most intriguingly, some theories suggest that intelligent life might eventually learn to harness or even manipulate dark energy itself. Advanced civilizations billions of years in the future might develop technologies that can tap into the cosmic expansion, using dark energy as a source of power or even as a means of cosmic engineering on the grandest possible scale. As you surrender to sleep, imagine yourself carried forward through cosmic time by the gentle current of dark energy expansion. You drift through eons, unimaginable, witnessing the slow evolution of cosmic structure, the patient work of stellar nucleosynthesis, the gradual cooling of the universe, all guided by the mysterious force that permeates every cubic centimeter of space. As consciousness fades and dreams begin to form, let your final thoughts rest on the profound mystery that dark energy represents. This invisible force comprising the majority of our universe reminds us that reality extends far beyond our direct perception, that the cosmos holds secrets we are only beginning to glimpse. The search for dark energy's true nature connects us to the deepest questions about existence itself. What is the fundamental fabric of space-time? Why does empty space possess energy? How are the smallest scales of quantum mechanics connected to the largest scales of cosmic evolution? These questions may not have answers within our current scientific paradigms, pointing toward new physics that awaits discovery. In contemplating dark energy, we confront our cosmic humility. Despite our technological sophistication and mathematical prowess, we find ourselves embedded in a universe whose most basic properties remain deeply mysterious. The force that will determine the fate of everything we know reveals itself only through its effects on the largest scales of space and time. Yet there is something profoundly beautiful about this cosmic mystery. Dark energy connects the quantum foam at the smallest scales to the expansion of space at the largest scales, potentially unifying phenomena that seem completely separate in our everyday experience. It suggests that the universe possesses a hidden elegance, a deep mathematical structure that we are gradually learning to perceive. The ongoing quest to understand dark energy represents humanity at its most ambitious and curious. Around the world, scientists dedicate their lives to mapping the invisible architecture of reality, using the entire observable universe as their laboratory. They are cosmic explorers pushing into territories that dwarf all previous human discoveries, seeking to understand forces that operate on scales almost beyond comprehension. As you rest in the embrace of approaching sleep, feel yourself floating in the gentle current of cosmic expansion. Dark energy surrounds you, permeates you, carries you along on the universe's grand journey toward an uncertain but magnificent destiny. You are temporarily borrowing consciousness from the cosmos itself, briefly focusing cosmic awareness to contemplate its own nature. The same force that stretches space between distant galaxies also exists in the room around you, in the space between atoms in your body, in the quantum vacuum that underlies all of reality. You are immersed in the medium of cosmic evolution itself, riding the wave of universal expansion that began with the Big Bang and will continue until the universe reaches its final state. As you settle into comfort, imagine floating peacefully through the vast expanse of space. The stars twinkle like distant diamonds against the velvet darkness, but what you're seeing represents only a tiny fraction of what actually exists. Around you, invisible and silent, flows an ocean of mystery that makes up most of our universe. This invisible ocean is composed of two enigmatic entities, dark matter and dark energy. Together they account for approximately 95% of everything that exists, yet they remain largely hidden from our direct observation. Like a gentle cosmic lullaby, these mysterious forces work tirelessly, shaping galaxies, guiding the dance of stars, and determining the ultimate destiny of all creation. Dark matter, making up about 27% of the universe, acts like an invisible scaffolding upon which all visible matter hangs. Picture it as a gossamer web stretched across the cosmos, so delicate you cannot see it, yet so strong it holds entire galaxies in its embrace. This ethereal substance doesn't emit light, doesn't absorb light, and doesn't interact with ordinary matter in ways we can easily detect. It's like a ghost that influences everything around it while remaining forever elusive. Dark energy, even more mysterious, comprises roughly 68% of the universe. If dark matter is the invisible scaffolding, then dark energy is the gentle but relentless force that pushes everything apart. Imagine it as a soft, constant breath that slowly inflates the cosmos, stretching the fabric of space itself, carrying galaxies away from each other like leaves on an ever-expanding pond. The story of these cosmic mysteries began nearly a century ago, when astronomers first noticed something peculiar about the way galaxies moved. Picture yourself as one of those early observers, peering through a telescope on a quiet night, measuring the rotation of distant spiral galaxies. You would expect the outer edges of these cosmic pinwheels to rotate more slowly than their centers, just as the outer planets in our solar system orbit more slowly than the inner ones. But that's not what astronomers found. The outer regions of galaxies were spinning far too fast, as if held in place by some invisible gravitational anchor. This was our first glimpse of dark matter, not through seeing it directly, but through witnessing its gravitational influence on the visible stars and gas around it. Decades later, in the 1990s, astronomers studying distant supernovae made another startling discovery. These stellar explosions, acting like cosmic lighthouses, revealed that the expansion of the universe was not slowing down as expected, but actually accelerating. This acceleration required a new form of energy, dark energy, pushing space itself apart with ever-increasing vigor. These discoveries were like finding footprints in cosmic sand, evidence of something present but unseen, shaping the universe in ways we were only beginning to understand. As you drift deeper into relaxation, let your mind wander through the realm of dark matter. This mysterious substance reveals itself only through its gravitational effects, like an invisible dancer whose presence is known only by the movement of their partner. Dark matter particles, if they exist as particles at all, are unlike anything in our everyday experience. They stream through your body, through the earth, through the stars, without leaving a trace. Billions of these ghostly particles may be passing through you right now, as you lie here, completely unnoticed, unimpeded by the ordinary matter that makes up your cells and bones. Scientists have proposed various candidates for dark matter particles. Perhaps they are WIMPs, weakly interacting massive particles, heavy yet elusive entities that rarely interact with ordinary matter. Or maybe they are axions, hypothetical particles, so light and ethereal they barely disturb the fabric of reality as they flow through it. Some theories suggest even more exotic possibilities: sterile neutrinos, dark photons, or particles that exist in hidden dimensions, parallel to our own. The gravitational influence of dark matter extends far beyond individual galaxies. It forms vast cosmic webs, invisible highways along which galaxies cluster and align. These dark matter filaments stretch across hundreds of millions of light years, creating a hidden architecture that gives structure to the entire observable universe. In computer simulations, scientists can map these dark matter structures, revealing a cosmos that looks like a vast neural network, with nodes of concentrated matter connected by delicate filaments. It's a pattern that suggests some deep, underlying order to the universe, a cosmic blueprint written in invisible. Now let your thoughts turn to dark energy, perhaps the most mysterious component of our cosmos. Unlike dark matter, which clumps together and helps build structure, dark energy appears to be perfectly smooth, uniformly distributed throughout space, working tirelessly to push everything apart. Imagine dark energy as a gentle but persistent force, like a soft wind that never stops blowing. This cosmic wind doesn't move objects through space, but rather stretches space itself, creating more room between galaxies, more distance between galaxy clusters, gradually diluting the matter density of the universe. The nature of dark energy remains one of the deepest puzzles in modern physics. It might be a property of space itself, what Einstein called the cosmological constant, a fundamental energy inherent in the vacuum of space. Every cubic centimeter of empty space would contain this energy, and as the universe expands and creates more space, it creates more dark energy, leading to an accelerating expansion. Alternatively, dark energy might be a dynamic field, similar to the fields that govern other fundamental forces, but operating on cosmic scales. This field, sometimes called quintessence, could vary in strength over time and space, potentially changing the fate of the universe in ways we cannot yet predict. Some theories propose even more exotic explanations. Perhaps dark energy is a sign that our understanding of gravity itself is incomplete, and what we interpret as dark energy is actually evidence of modifications to Einstein's theory of relativity on the largest scale. Or maybe dark energy is a manifestation of extra dimensions beyond the three spatial dimensions we experience directly. As you continue to relax, envision the cosmic web, the largest structure in the universe, shaped by the invisible hand of dark matter. This web began forming in the early universe, shortly after the Big Bang, when tiny quantum fluctuations in the distribution of matter began to grow under the influence of gravity. Dark matter, being immune to the electromagnetic forces that affect ordinary matter, could begin clumping together earlier than the hydrogen and helium that would eventually form stars. These dark matter clumps acted like gravitational seeds, drawing in ordinary matter and eventually leading to the formation of the first stars and galaxies. The process unfolded like a slow cosmic symphony. Over hundreds of millions of years, dark matter halos grew larger and more massive, becoming the gravitational foundations upon which galaxies would be built. Within these halos, ordinary matter could cool and condense, forming the first stars, which lit up the universe and began the process of creating heavier elements necessary for planets and life. This cosmic web continues to evolve to galaxies flow along the dark matter filaments, like cars on invisible highways, sometimes colliding and merging, sometimes being stripped apart by tidal forces. The Milky Way itself sits within a dark matter halo roughly 10 times more massive than all the visible stars it contains. Dark energy, meanwhile, works against this structure formation. As it accelerates the expansion of space, it makes it harder for gravity to pull matter together. In the far future, dark energy may become so dominant that it prevents the formation of new structures altogether, leaving the universe increasingly empty and cold. Let your mind drift now to the far future, where the interplay between dark matter and dark energy will determine the ultimate fate of everything we know. The story that unfolds depends on the nature of these mysterious components and how they evolve over cosmic time. If dark energy continues to behave as it does today, the universe will expand forever, growing larger, colder, and more dilute. The cosmic web of dark matter will stretch and thin. Galaxies will move apart until they disappear beyond each other's horizons, and the universe will enter what cosmologists call the Big Freeze. In this distant future, perhaps 100 billion years from now, the Milky Way and its neighboring galaxies will merge into a single massive, elliptical galaxy, surrounded by the vast emptiness of space. The cosmic microwave background, the afterglow of the Big Bang, will have cooled to nearly absolute zero, and the universe will be filled with nothing but isolated island galaxies drifting through the cosmic night. But the story doesn't end. Over even longer timescales, trillions upon trillions of years, the stars will burn out one by one, leaving behind white dwarfs, neutron stars, and black holes. The dark matter halos around these dead galaxies will gradually evaporate as their constituent particles are ejected into intergalactic space through gravitational interactions. If dark energy continues to strengthen, an even more dramatic fate awaits. In a scenario called the Big Rip, the acceleration of space becomes so extreme that it eventually overcomes all other forces. First, galaxy clusters would be torn apart, then individual galaxies, then solar systems, then planets, then atoms themselves. The fabric of space would expand so rapidly that it would rip apart the very structure of matter. Alternatively, if dark energy is not constant but evolves over time, other fates become possible. If dark energy weakens or even reverses sign, the expansion of the universe could slow, stop, and reverse, leading to a big crunch, where everything collapses back into a singularity. Or dark energy might oscillate, leading to cycles of. These invisible forces have played crucial roles in creating the cosmic environment that allowed stars, planets, and ultimately life to exist. Dark matter provided the gravitational scaffolding that allowed the first structures to form in the early universe. Without dark matter, the tiny density fluctuations left over from the Big Bang would not have grown large enough to create stars and galaxies. The universe might have remained a thin, nearly uniform soup of hydrogen and helium, forever dark and lifeless. The specific properties of dark matter also matter for life. If dark matter interacted too strongly with ordinary matter, it might have prevented gas from cooling and condensing into stars. If it were too weakly interacting, it might not have provided enough gravitational pull to form the structures we observe. The dark matter in our universe seems to have just the right properties to enable structure formation, while allowing stars to form within those structures. Dark energy, too, has played a crucial role in life's story, though its influence is more subtle and long-term. If dark energy were much stronger than it is, the universe would have expanded too rapidly for galaxies to form at all. If it were much weaker, the universe might have collapsed back on itself before there was time for stars to evolve and create the heavy elements necessary for rocky planets and complex chemistry. The timing of dark energy's dominance is also significant. Dark energy became the dominant component of the universe only relatively recently in cosmic history, allowing billions of years for stars to form, live their lives, and seed the cosmos with heavy elements. If dark energy had dominated earlier, the universe might have entered its acceleration phase before complex structures could develop. This delicate balance suggests that we live in a universe whose fundamental properties have finely tuned for the emergence of complexity and life. Whether this fine-tuning is the result of physical necessity, cosmic selection effects, or something even more mysterious, remains one of the deepest questions in cosmology. As your breathing slows and deepens, let your thoughts turn to humanity's ongoing quest to understand these cosmic mysteries. Despite decades of research, dark matter and dark energy remain largely enigmatic, revealing themselves only through their gravitational effects and their influence on the expansion of space. Our evidence for dark matter comes from multiple, independent observations. We see its gravitational effects on galaxy rotation curves, galaxy cluster dynamics, and gravitational lensing, the bending of light around massive objects. We observe its influence on the cosmic microwave background and the large-scale structure of the universe. Computer simulations that include dark matter can reproduce the observed patterns of galaxy distribution, while those without dark matter fail dramatically. Yet despite this compelling evidence, we have never directly detected a dark matter particle. Deep underground laboratories house sensitive detectors, hoping to catch the rare collision of a dark matter particle with ordinary matter. Particle accelerators smash protons together at enormous energies, searching for signs of dark matter creation. Space-based telescopes look for the gamma rays that might be produced when dark matter particles annihilate each other. Our understanding of dark energy is even more limited. We know it exists because we can measure its effects on the expansion of the universe using distant supernovae, the cosmic microwave background, and the large-scale distribution of galaxies. But we have no direct way to study dark energy in the laboratory or to probe its fundamental nature. Current and future astronomical surveys are mapping the universe in unprecedented detail, hoping to reveal clues about the nature of dark energy. Projects like the Dark Energy Survey, the Euclid space mission, and the upcoming Vera Rubin Observatory will measure the positions and distances of billions of galaxies, tracking how the expansion of the universe has evolved over cosmic time. As you settle into the deepest states of relaxation, reflect on the profound journey of discovery that continues to unfold around these cosmic mysteries. Scientists around the world work tirelessly, using the most advanced tools and theories available to glimpse the true nature of the invisible universe. New theoretical frameworks are being developed to explain dark matter and dark energy. String theory suggests that these phenomena might be manifestations of extra dimensions or exotic particles, predicted by theories of quantum gravity. Loop quantum gravity proposes that space itself might have a granular structure that could explain dark energy. Modified theories of gravity attempt to explain the observations without invoking new forms of matter or energy. Experimental efforts continue to push the boundaries of detection sensitivity. Next-generation dark matter detectors will be larger and more sensitive than ever before, capable of detecting increasingly rare interactions. New particle accelerators may probe energy scales where dark matter particles might be produced and studied directly. Astronomical observations will become ever more precise and comprehensive. Future space missions will map the cosmic web in 3 dimensions, measure the properties of dark energy with unprecedented accuracy, and perhaps reveal new phenomena that we haven't yet imagined. The quest to understand dark matter and dark energy represents more than just scientific curiosity. These mysteries touch on the most fundamental questions about the nature of reality, the origin and fate of the universe, and our place within the cosmic story. They remind us that despite all our technological achievements and scientific knowledge, we still inhabit a universe full of wonder and mystery. In the quiet darkness of your rest, you are connected to these cosmic mysteries. The same dark matter that shapes galaxies flows through the space around you. The same dark energy that drives the expansion of the universe is operating in the very fabric of space-time beneath your sleeping form. You are part of this grand cosmic story, a conscious observer in a universe that is far stranger and more wonderful than our ancestors ever imagined. As you drift towards sleep, carry with you the sense of wonder that comes from contemplating these cosmic enigmas. Dark matter and dark energy remind us that the universe is far from fully understood, that mystery and discovery await us at every turn. These invisible forces that dominate our cosmos serve as a humbling reminder of how much we still don't know. They challenge our assumptions about the nature of matter, energy, space, and time. They push us to develop new theories, build new instruments, and ask new questions about the fundamental workings of reality. The story of dark matter and dark energy is still being written. Future generations may look back on our current understanding as quaint and incomplete, just as we now view the cosmologies of centuries past. Or perhaps these mysteries will persist, eternal reminders that the universe will always hold secrets beyond our comprehension. In the gentle embrace of sleep, let your mind rest in the vastness of the cosmic mystery. Dream of invisible oceans of dark matter flowing through space, of dark energy stretching the fabric of reality itself, of galaxies dancing their slow waltz across billions of years. Rest in the knowledge that you are part of something infinitely larger and more mysterious than everyday experience suggests, a universe where the greatest discoveries may still lie ahead, waiting in the darkness to be revealed. The cosmos keeps its secrets well, but it also offers glimpses of truth to those patient and curious enough to. As you sleep, the invisible universe continues its ancient dance, dark matter and dark energy playing their mysterious roles in the grandest story ever told, the story of everything that is, was, and ever will be. Sleep well, cosmic traveler. The universe watches over your dreams with the patience of dark matter and the infinite gentleness of dark energy, stretching space itself to make room for your rest. Sweet dreams under infinite stars, visible and invisible, in a cosmos that holds you with love too vast to comprehend and too gentle to fear.